Hey everyone, Professor Michael Scanlan here. In today's video, we're going to look at more interactions between electricity and magnetism. We're even going to get down to a very small scale to try to show some pretty interesting magnetic properties of some materials. First though, let's take a look at how magnetic forces are exerted on electric currents. Let's see the setup that we have. I have a conducting wire, that's this thing, and it's connected to my power supply over here, okay? And as you can see, the power supply is off. It's free to move, okay? Well, Professor Scanlan, what's this thing? This is a ridiculously powerful magnet. This thing is very, very, very strong, okay? So this is not something that I would necessarily want to put my phone next to or anything like that. So this is a very strong magnet. And so what I'm going to do is I'm going to put an electric current through this wire that's sitting in this magnetic field. And what we'll see is that magnetic fields exert forces on moving charges. In this case, this electric current, moving electric charges. All right, let's take a look and see what happens. So turn it on, and the final knob, watch the hanging wire. All because it's got an electric current in it. Now, what would happen if I reverse the wires? Reverse the polarity here. Let's turn it on and see. So the first case it went forward. I bet this time it goes backwards. Sure enough. I may have done this once or twice before. So there you go, magnetic forces, magnetic fields exerting forces on moving electric currents. Let's take a look at something else we can do with this magnet that I think you'll really enjoy. In this next segment, we're going to look at something called eddy currents. Now, eddy currents are produced whenever a magnetic field induces a current, okay? So let's take a look at the setup that we have here. All right, so I have an aluminum paddle, and if we remember, aluminum, here's my magnet, is not a magnetic material, okay, at all. So let me put back on here. Now it hooks onto this bar and it's able to swing back and forth without any issues. I have here the ridiculously powerful magnet, and I'm going to try to line it up to be in the middle here. There we go. So the magnet, the paddle is hanging right in the middle of the magnet. And I want you to watch what happens whenever I pull it back and then let it go. Remember, it's not being attracted to that magnet. Let's watch that again. One of my students, when I did this in class, was, they shot up. They were paying halfway close attention, let's say, and thought their eyes were playing tricks on them as they nodded off. Here's one that's a little bit different. It's got slots in it. We're gonna pull it back, and is it gonna do the same thing because it's got these holes in it? Surely that makes a difference. Lo and behold, what's happening? As this conductor, this electrical conductor, passes into this magnetic field, it's a changing magnetic field that's gonna set up an eddy current in this thing that is going to interact with the magnetic field that created it. I want you to take a look at some resources, see what you can find on eddy currents. Right now though, let's take a look at probably one of my favorite demonstrations dealing with magnetism. So what do we have here? I have our very strong magnet again. I have a small rod of glass hanging by a thin string. Now I've let it wind and unwind itself so that it's kind of hanging in equilibrium as much as possible. Now, true or false? Glass is attracted to magnets, or magnets are attracted to the glass. Well, false, right? We wouldn't say that glass is necessarily a magnetic material. What we mean by that is it's not ferromagnetic. Glass has a property known as diamagnetism. It is a diamagnetic material. Diamagnetic materials, in fact, pretty much everything has some diamagnetic properties. Just other properties tend to kind of overwhelm them. Water is diamagnetic. You get a pretty cool effect. I'm going to mention it in just a second. So diamagnetic materials really hate magnetic fields. They don't like them in the least. And what will happen is, think of a stone in the river. The water kind of just goes around it. The magnetic field just kind of goes around it and exerts forces on it. What's happening in a diamagnetic material is your electrons are all paired. As a general rule of thumb, if the electrons in your compound all have pairs, then it's probably going to be mostly diamagnetic. That's not a strict by the book rule, it's just kind of a general guideline. So watch what happens if I turn just the magnet. Now glass is not a ferromagnetic material. It's not attracted to a magnet at all. But as you can see, it is responding to this magnetic field. It's not touching the magnet itself. The glass is staying perpendicular to the magnetic field. The magnetic field is running across these two magnets, between these two magnets, pretty much straight, relatively straight. And that glass rod is orienting itself perpendicular to that field as we go. It is diamagnetic. It's getting as away from that field as much as possible. Pretty cool, huh? Now, let's take a look at another type of material. All right, so this time, instead of a piece of glass, I've got a piece of aluminum hanging by a thin string in our magnet. Now, aluminum is not ferromagnetic, as we've seen. It's not attracted to magnets in the traditional sense. It's not diamagnetic, because if it were diamagnetic, it would be pointing perpendicular to the field, but look how it is. It's aligning with the field. And if we rotate the magnet, you'll notice the aluminum rotates with it, staying in that magnetic field. In paramagnetic materials, our rule of thumb goes, if not all of the electrons in the atom or molecule are paired, then they will align with the magnetic field instead of aligning against the magnetic field like a diamagnetic material, and they will respond to it by lining up with it. So it's very similar to ferromagnetism, in which case would be like iron, nickel, or cobalt. Your refrigerator magnets are ferromagnetic. This is a weak kind of cousin of that. Now, because of the temperature, the thermal properties of the material, as soon as I move the magnet away, the electrons are going to misalign all over again, and they're going to do their own thing. Ferromagnetic materials, though, watch, it's going to turn and align itself. Ferromagnetic materials tend to maintain their magnetic properties just a little bit after being magnetized. Paramagnetic materials, it's pretty much once it's done, until you put it back in the magnetic field again. So there you go. You have ferromagnetism, diamagnetism, and paramagnetism, and they all depend on what is happening at what we would call a quantum level in the electron shells of atoms and molecules. So it's the electrons, very, very itty-bitty small things in their motions and their behaviors and their interactions, that are what we perceive and what we see and measure and deal with when it comes to magnetism. They're the ones responsible. So there you go, some pretty cool demonstrations dealing with magnetism and electricity. We even got to talk about electrons, and I said quantum. Read up some more on paramagnetism, diamagnetism, ferromagnetism if you're interested. We'll post some links. And eddy currents too. That's all for today's video. Thanks for watching, everyone.